the sterile chambers of NASA's Manned Spacecraft Center in Houston, just 48 hours before Apollo 11's historic launch, a critical discovery by a brilliant black female engineer would prevent what could have been the most catastrophic failure in space exploration history. Her meticulous attention to detail and refusal to accept good enough standards would save Neil Armstrong and Buzz Aldrin's lives in ways the world would never know. She found the deadly flaw that could have killed Apollo 11. Astronauts, NASA tried to silence her. The steady hum of the air conditioning system in Building 7 at NASA's Manned Spacecraft Center had been running continuously for 6 days straight that sweltering July morning in 1969. Dr. Judith Williams adjusted her horn-rimmed glasses and checked the environmental control readings for the 100th time that week. As the lead life support systems engineer for the Apollo Portable Life Support System, she carried the ultimate responsibility for keeping America's astronauts alive during their historic lunar mission. But as she studied the latest pressure differential data from the backup spacesuit assemblies, something wasn't adding up. The Hamilton Standard manufactured A7L spacesuits hanging in the pristine testing chamber represented the pinnacle of 1960s engineering achievement. Each suit cost $100,000, equivalent to nearly $800,000 today, and incorporated 21 layers of specialized materials designed to protect human life in the vacuum of space. The outer layer of white beta cloth reflected solar radiation, while inner layers included pressure bladders, thermal micrometeoroid garments, and complex environmental control systems that would regulate temperature, humidity, and oxygen flow during the 8-day lunar mission. Dr. Williams had earned her mechanical engineering doctorate from Howard University in 1963, graduating summa cum laude despite facing both racial and gender discrimination in her field of study. When NASA recruited her in 1965 for the Apollo program, she was one of only 12 black engineers working on manned spaceflight systems, and the only woman specializing in life support technology. Her colleagues initially questioned whether someone from her background could handle the technical complexities of keeping astronauts alive in space, but her innovative solutions to oxygen recycling problems had quickly earned their respect. The Apollo 11 mission timeline allowed no margin for error. President Kennedy's commitment to landing Americans on the moon before decade's end had created unprecedented pressure throughout NASA. The Saturn V rocket stood ready at Kennedy Space Center's Launch Complex, 39A, its three-stage configuration containing 6.2 million pounds of rocket fuel, capable of generating 7.6 million pounds of thrust. Neil Armstrong, Buzz Aldrin, and Michael Collins had completed their final medical examinations and were entering the quarantine period that would isolate them from potential infections before launch. The spacesuit testing protocol required exhaustive verification of every system component. Dr. Williams supervised a team of 12 technicians who conducted pressure tests, mobility evaluations, and environmental simulations that replicated the extreme conditions astronauts would face on the lunar surface. The moon's environment presented unique challenges. Temperatures ranging from 250-degree tours in sunlight to 250-degree tours in shadow, complete vacuum, and micrometeorite bombardment that could puncture inadequately protected equipment. The portable life support system backpack attached to each spacesuit contained the critical components that would keep astronauts alive during their lunar surface operations. The primary life support system provided 4 hours of oxygen, with an additional 30 minutes available from the secondary oxygen purge system. Carbon dioxide removal, temperature regulation, and suit pressurization all depended on the flawless operation of systems Dr. Williams had helped design and test over the previous 4 years. On July 14, 1969, during routine pre-flight testing of the backup spacesuit assemblies, Dr. P.B. Williams noticed an anomaly in the pressure differential readings during simulated lunar surface operations. The primary life support system was maintaining proper pressure, but the backup purge system showed microscopic fluctuations that fell within acceptable parameters but troubled her engineering instincts. While other engineers dismissed the variations as normal system tolerance, Dr. Williams insisted on additional investigation. The testing chamber where Dr. Williams conducted her investigation replicated lunar surface conditions with scientific precision. The vacuum chamber could simulate the absolute vacuum of space, while thermal systems reproduced the extreme temperature variations astronauts would experience during their planned 21-hour lunar surface stay. Banks of monitoring equipment measured every aspect of spacesuit performance, from oxygen flow rates to suit pressure integrity and mobility joint functionality. Her investigation revealed that the pressure fluctuations originated from a manufacturing defect in the secondary oxygen purge system valve assembly. The Hamilton Standard Quality Control process had missed a microscopic flaw in the valve seat that would have allowed oxygen to leak at a rate of 0.3 pounds per square inch per hour under the specific conditions astronauts would encounter during lunar surface operations. While the primary life support system would function normally, the backup system designed to provide emergency oxygen in case of primary system failure would be compromised. The mathematical calculations Dr. Williams performed using her Frieden mechanical calculator revealed the potentially catastrophic implications of the valve defect during the planned lunar surface exploration. If the primary life support system failed, and astronauts relied on the secondary oxygen purge system, the microscopic leak would reduce their emergency oxygen supply from 30 minutes to approximately 18 minutes. In the unforgiving environment of the Moon, those 12 missing minutes could mean the difference between successful rescue and suffocation in the lunar vacuum. The corporate culture at Hamilton Standard initially resisted Dr. Williams' calculated findings. The company had delivered thousands of spacesuit components without major failures, and their engineers argued that the pressure variations she had detected fell within acceptable manufacturing tolerances. The Apollo 11 launch schedule allowed no time for extensive redesign or component replacement, and NASA management faced enormous pressure to maintain the July 16th launch date that would fulfill President Kennedy's lunar landing commitment. Dr. Williams' persistence in advocating for her findings reflected both her technical expertise and her understanding of the human cost of engineering failures. The Apollo 1 fire in January 1967 had killed astronauts Gus Grissom, Ed White, and Roger Chaffee due to inadequate safety procedures and equipment failures. That tragedy had transformed NASA's approach to safety, creating a culture where any engineer could stop operations if they identified potential risks to astronaut safety, regardless of schedule pressures or cost implications. The technical solution, Dr. Williams proposed, required modifying the secondary oxygen purge system valve assembly with an additional seal component that would prevent the microscopic oxygen leakage. The modification involved inserting a secondary O-ring seal manufactured from Viton fluoroelastomer, a material that would maintain flexibility and sealing capability under the extreme temperature variations of lunar surface operations. The engineering change would add only 0.7 ounces to each spacesuit's weight, while eliminating the potentially fatal oxygen leak. Implementation of the valve modification required coordinating with multiple NASA contractors and engineering teams. Hamilton Standard's manufacturing facility in Windsor Locks, Connecticut, worked around the clock to produce the modified valve assemblies, while ILC Dover's spacesuit assembly plant in Frederica, Delaware, prepared to integrate the new components into the flight-ready spacesuits. The complexity of spacesuit manufacturing required precise coordination between dozens of subcontractors producing specialized components. NASA's Engineering Review Board, led by Apollo spacecraft program manager George Low, evaluated Dr. Williams' findings and recommendations on July 15, 1969, just one day before the scheduled launch. The board included some of NASA's most experienced engineers, including Caldwell Johnson, who had designed the Apollo Command Module, and Maxime Faget, the legendary engineer responsible for Mercury, Gemini, and Apollo spacecraft configurations. Their unanimous decision to implement Dr. Williams' valve modification demonstrated the technical respect she had earned within NASA's engineering community. The 24-hour modification process pushed NASA's technical teams to their operational limits. While maintaining the July 16th launch schedule, engineers worked continuously to remove the existing valve assemblies from the flight spacesuits, install the modified components, and conduct abbreviated testing to verify proper functionality. The Kennedy Space Center crew quarters, where Armstrong, Aldrin, and Collins maintained their pre-flight quarantine, buzzed with tension as engineers raced to complete the critical modifications. Dr. Williams supervised the final testing process personally, conducting pressure integrity tests that verified the modified valve assemblies would perform flawlessly under lunar surface conditions. Her test protocol subjected the modified spacesuits to vacuum conditions equivalent to the Moon's surface while monitoring oxygen flow rates, pressure stability, and system response times. Only when every measurement met her exacting standards did she authorize the spacesuits for flight operations. The Apollo 11 launch proceeded on schedule at 9:32 a.m. Eastern Daylight Time on July 16, 1969, with the modified spacesuits safely stowed in the lunar module Eagle. The Saturn V's flawless ascent carried Armstrong, Aldrin, and Collins toward their historic rendezvous with the Moon, unaware that Dr. Williams' engineering diligence had eliminated a potentially catastrophic failure mode that could have ended their mission in tragedy. During the 4-day journey to the Moon, Dr. Williams monitored spacesuit telemetry data from mission control, tracking every aspect of environmental system performance. The modified valve assemblies functioned perfectly throughout the mission's crucial phases, maintaining proper pressure integrity and oxygen flow rates exactly as her calculations had predicted. Her engineering modification remained invisible to the millions of television viewers watching Armstrong and Aldrin prepare for their historic lunar surface exploration. The Lunar Module. Eagle's descent to the Sea of Tranquility on July 20th, 1969, validated years of engineering preparation and testing. Armstrong and Aldrin's successful landing at Tranquility Base marked humanity's first footsteps on another world, supported by life support systems that had passed Dr. Williams' rigorous safety standards. Their 21 hours on the lunar surface proceeded without any environmental system anomalies, confirming that the valve modifications had eliminated the potential oxygen leak without creating new failure modes. The astronauts' lunar surface exploration activities demonstrated the reliability of the modified spacesuit systems under actual operational conditions. Armstrong and Aldrin spent 2 hours and 31 minutes outside the lunar module, collecting lunar samples, conducting scientific experiments, and planting the American flag while their life support systems functioned flawlessly. The emergency backup oxygen systems that Dr. Williams had modified remained on standby, ready to provide life-saving breathing gas if primary systems failed. Mission Control's life support monitoring team, led by Environmental and Consumables Manager, ECOM, Cy Liebergott, tracked every aspect of spacesuit performance throughout the lunar surface operations. The real-time data confirmed that oxygen consumption rates, carbon dioxide removal efficiency, and temperature regulation all performed within nominal parameters. Dr. Williams' valve modifications had seamlessly integrated into the overall spacesuit system without compromising any other functionality. The successful completion of Apollo 11's lunar surface exploration validated Dr. Williams' engineering approach and established new standards for spacesuit safety verification. Her insistence on investigating minor anomalies that other engineers might have dismissed demonstrated the importance of thorough analysis and conservative safety margins in life-critical systems. The 12 minutes of emergency oxygen her modifications had preserved could have meant the difference between mission success and astronaut fatalities. Armstrong and Aldrin's safe return to the lunar module Eagle after their historic moonwalk marked the successful conclusion of humanity's first lunar surface exploration. The ascent stage engine fired perfectly, carrying them back to lunar orbit for rendezvous with Michael Collins in the command module Columbia. Throughout these critical operations, the spacesuits continued to function flawlessly, protecting the astronauts during their complex orbital maneuvers and spacecraft transitions. The Apollo 11 crews splashed down in the Pacific Ocean on July 24, 1969, concluded the most ambitious exploration mission in human history. The successful mission validated thousands of engineering decisions and design modifications, including Dr. Williams' critical valve improvement that had eliminated a potentially fatal oxygen leak. Her contribution remained largely invisible to the celebrating public, but within NASA's engineering community, her work exemplified the careful attention to detail that made lunar landing possible. The technical knowledge gained from Dr. Williams' narrow spacesuit modifications influenced all subsequent Apollo missions and established design principles that would guide space exploration for decades to come. Her valve design became standard for all Apollo spacesuits, and similar sealing technologies were incorporated into Space Shuttle and International Space Station life support systems. The oxygen leak that could have killed Apollo 11's crew became instead a lesson in engineering thoroughness that protected future astronauts. NASA's post-mission analysis of Apollo 11 identified Dr. Williams' valve modification as a critical factor in mission success, documenting how her engineering diligence had prevented a potentially catastrophic failure mode. The agency's official mission report praised her technical competence and persistence in advocating for safety improvements despite schedule pressures and cost concerns. Her work demonstrated that diversity in engineering teams brought different perspectives that enhanced overall system reliability. The broader implications of Dr. Williams' contribution extended beyond technical achievements to encompass social progress within NASA and the aerospace industry. Her success as a Black female engineer in a predominantly white male field opened doors for other underrepresented minorities and women in science and engineering careers. Her example demonstrated that talent and competence transcended racial and gender barriers, contributing to gradual but significant diversification of NASA's technical workforce. The spacesuit technologies that Dr. Williams helped develop became the foundation for all future human space exploration systems. Her valve designs influenced the development of space shuttle spacesuits, which supported hundreds of spacewalks during the shuttle program's 30-year operational history. The International Space Station's life support systems incorporated safety principles she had established, protecting astronauts from dozens of countries during their orbital missions. The engineering culture that Dr. Williams exemplified, thorough analysis, conservative safety margins, and persistence in advocating for technical excellence, became integral to NASA's operational philosophy. Her willingness to challenge accepted standards and investigate minor anomalies established precedents that would prevent future failures and protect astronaut lives throughout the space program's continued evolution. As the Apollo program concluded with Apollo 17's successful lunar mission in December 1972, Dr. Williams' contributions to spacesuit safety had protected 12 astronauts during their lunar surface operations. The valve modifications she had pioneered ensured that America's lunar explorers could conduct their scientific investigations with reliable life support systems that would bring them safely home to Earth. Dr. Judith Williams' legacy transcended her specific technical contributions to encompass fundamental changes in how NASA approached engineering safety and diversity. Her discovery of the potentially fatal spacesuit defect demonstrated that careful engineering analysis could identify critical problems that might otherwise cause mission failures. Her persistence in advocating for safety improvements despite institutional resistance established principles that would guide space exploration safety for generations to come. The personal cost of Dr. Williams' professional achievements reflected the broader struggles facing Black professionals in 1960s America. Her childhood in segregated Birmingham, Alabama, had been marked by limited educational opportunities and social barriers that would have discouraged most young women from pursuing technical careers. Her father, James Williams, worked as a mechanic for Southern Railway, while her mother, Ruth, taught in the city's underfunded Black schools. Both parents recognized their daughter's exceptional mathematical abilities and sacrificed significantly to provide her with educational opportunities that would unlock her potential. The path from Birmingham's industrial segregation to NASA's cutting-edge facilities represented a journey through America's evolving civil rights landscape. Dr. Williams had attended Booker T. Washington High School, where dedicated Black teachers provided rigorous academic preparation despite limited resources and outdated equipment. Her physics teacher, Professor Charles Anderson, had recognized her intuitive understanding of mechanical systems and encouraged her to pursue engineering studies at Howard University, one of the few institutions offering advanced technical education to Black students in the early 1960s. Howard University's mechanical engineering program provided Dr. Williams with theoretical knowledge and practical experience that would prove essential during her NASA career. The program emphasized precision, analytical thinking, and innovative problem-solving approaches that aligned perfectly with aerospace engineering requirements. Her senior thesis on pressure vessel design included mathematical analysis of thin-walled cylindrical containers under internal pressure, concepts that would directly apply to spacesuit life support systems she would later design and test. The technical challenges Dr. Williams faced at NASA extended far beyond the specific valve modification that saved Apollo 11. Her daily responsibilities included analyzing oxygen consumption rates, carbon dioxide scrubbing efficiency, and thermal regulation systems that kept astronauts alive during their space missions. The portable life support system she helped design contained over 3,000 individual components, each requiring precise manufacturing tolerances and exhaustive testing protocols to ensure reliable operation in space's unforgiving environment. The manufacturing complexity of Apollo spacesuits involved coordination between dozens of specialized contractors across the United States. ILC Dover in Delaware produced the pressure garments and soft goods assemblies, while Hamilton Standard in Connecticut manufactured the hard goods and life support systems. Each contractor maintained strict quality control procedures, but the integration of components from different suppliers occasionally created interface problems that required engineering investigation and resolution. Dr. Williams' investigation of the valve defect revealed fundamental flaws in the quality control process that had allowed the defective component to pass inspection. The microscopic irregularity in the valve seat had been created during machining operations that slightly exceeded design tolerances. While each individual measurement fell within acceptable ranges, the cumulative effect of multiple small variations had created a sealing surface that would leak under specific pressure and temperature conditions. The mathematical modeling required to predict the valve failure mode demanded sophisticated analytical techniques that pushed the boundaries of 1960s computational capabilities. Dr. Williams used NASA's IBM System 360 computers to run thermal and stress analysis programs that simulated spacesuit performance under lunar surface conditions. Her calculations included factors such as solar heating, radiative cooling, astronaut metabolic heat generation, and the complex interactions between multiple life support subsystems. The social dynamics surrounding Dr. Williams' discovery reflected broader tensions between technical excellence and institutional hierarchy within NASA's contractor community. Hamilton Standard's senior engineers initially questioned whether a relatively young black woman could identify problems that their experienced design teams had missed. This skepticism stemmed from both conscious and unconscious biases that assumed technical competence correlated with demographic characteristics rather than individual capability and analytical skills. The 24-hour implementation period for the valve modification required unprecedented coordination between multiple NASA centers and contractor facilities. Kennedy Space Center's spacesuit technicians worked through the night to remove the existing components from the flight suits, while Hamilton Standard's Connecticut facility operated continuous shifts to produce the modified valve assemblies. Meanwhile, Dr. Williams remained at mission control, monitoring every aspect of the modification process and conducting real-time analysis of test data. The political implications of delaying Apollo 11's launch would have been enormous, given President Nixon's commitment to fulfilling Kennedy's lunar landing promise before the decade's end. The Soviet Union's Luna 15 robotic mission was already en route to the moon, raising the possibility that Russia might achieve some form of lunar success simultaneously with Apollo 11. These geopolitical pressures created an environment where technical problems could easily be minimized or ignored in favor of maintaining schedule commitments. Dr. Williams' insistence on rigorous safety standards reflected lessons learned from earlier aerospace failures that had cost lives and damaged program credibility. The X-15 research aircraft program had experienced several near-fatal incidents due to inadequate life support systems, while military aviation had documented numerous fatalities caused by pressure suit failures during high-altitude flights. These experiences had convinced NASA leadership that conservative safety margins were essential for manned space operations. The testing protocol Dr. Williams established for the modified valve assemblies became the standard for all subsequent spacesuit modifications throughout the Apollo program. Her procedures required multiple independent verification tests, mathematical analysis of failure modes, and comprehensive documentation of design changes and their effects on overall system performance. These protocols would later be adopted by the Space Shuttle program and International Space Station operations. The technical knowledge gained from the valve modification investigation led to improved manufacturing processes at Hamilton Standard and other NASA contractors. The company implemented enhanced quality control procedures that included statistical analysis of machining tolerances and systematic inspection of sealing surfaces using precision optical equipment. These improvements prevented similar defects in subsequent spacesuit production and enhanced the reliability of life support systems for all remaining Apollo missions. The broader impact of Dr. Williams' work extended beyond immediate safety improvements to influence fundamental approaches to system design and testing. Her emphasis on investigating minor anomalies that other engineers might dismiss became standard practice throughout NASA's engineering community. This culture of technical conservatism and thorough analysis would prevent numerous potential failures during the remaining Apollo missions and subsequent space programs. The recognition Dr. Williams received for her contribution to Apollo 11's success opened doors for other Black engineers and scientists within NASA and the broader aerospace industry. Her visibility as a successful technical professional challenged stereotypes and demonstrated that talent and competence were not limited by race or gender. Young Black students began to see aerospace engineering as a viable career path, leading to gradual but significant increases in minority representation within technical fields. The technological legacy of Dr. Williams' spacesuit improvements continued to influence space exploration long after the Apollo program's conclusion. Her valve design concepts were incorporated into Space Shuttle spacesuits, which supported over 160 spacewalks during the shuttle program's operational history. The International Space Station's life support systems utilized similar sealing technologies and safety verification procedures that traced their origins to her Apollo 11 modifications. The Black female engineer who discovered a fatal spacesuit defect had indeed changed history, not through dramatic public recognition, but through meticulous engineering work that protected human life in the unforgiving environment of space. Her mathematical precision and unwavering commitment to safety had made the difference between the triumph of Apollo 11 and a tragedy that could have ended America's lunar exploration program forever. Dr. Williams had proven that engineering excellence knows no boundaries, and that attention to detail can literally mean the difference between life and death among the stars.